Hey everyone. So today we'll be discussing a problem on Sphere Online Judge. The problem name is tree degree, degree of a tree. So we will first understand the problem statement, the ways, the approach to do that, the input output, and then I will quickly jump to the solution, how to implement the approach that I discuss. So let's go to the problem. So the problem is that a user always represents the rooted trees in a simple array. First, the array holds four conditions. Okay, so there are four conditions uh, based on which a tree is represented in a array format. So we will see how it will be represented. So the first condition is if the tree has n vertices, the array has length 2n. Second, each vertex has a number from 1 to n, which is written twice, but they may not be necessarily beside each other. Okay, so let's see this example and see based on these two conditions first how it is represented. So if you see, if the tree has n vertices, here in this example, the tree has 5 vertices. So if you see the structure, how this is made, so there are total 10 elements. So this condition fulfills. Second condition, if a tree has a number, each vertex has a number from 1 to n, which is written twice. So if you see, let's say this 1. So 1 is written here and then 1 is written here. Again, let's take another example for, let's say, 5. So 5 is written here and then here. It means each vertex has been repeated twice in the array, either by each other, beside each other, or at a distance. Okay. So the third condition is between the number of each vertex, the numbers on its subtrees are written. So what it means that if you see 1 has the subtree of this, like 3, 4, 5, and 2 are its subtrees, basically. So if you see 1 and 1, this one start and end is wrapping over this sub array part. So if you see 3, 2, 4, 5 are the sub arrays. Okay. If you see 3, so 3 starts over here and 3 ends over here. So between this 3 and 5, 3 start 3 and end 3, whatever the elements are, they are its subtrees. For example, 3 subtrees are 4, 5, and 2. So why 1 is not a subtree? Because 1 is the root, 1 is the parent. So 1 is the parent, one's child is 3, one's child is 3 over here. And then again, if we take about 3, three's children are 4, 5, and 2. 4, 5, and 2 are subtrees. So basically, 4, 5, and 2 are written inside this starting and ending of 3. Okay, so this one was point number 3. And point number 4 is vertex 1 is always the root of the tree. So if you see in all the cases, this tree, this graph can be represented by these all the ways. Okay. And in all the conditions, you can see that 1 is at start and end. It means 1 will always be the root and all the other elements will be the subtree of that tree. Okay. Subtree of the root element. Okay. Again, since it is written that if you see this example, this tree can be represented in these 6 ways. Okay, let's quickly see any of the other way how it is represented and does this hold true for this example. So if you see 1, 1. So 1 is the root of the tree, 1 is the root of the tree. 1 is wrapping these elements 3, 2, 5, and 4. Are 3, 2, 5, and 4 are subtrees of 1? Yes. Then if you see that all the 2, 5, and 4 are wrapped by the starting and ending of this 3. It means 2, 5, 4 are subtrees of 3. Is it true? Yes. It means that whatever is the first element, whatever is the starting and ending of the element inside that array will be the subtrees of that. Okay. So this is how a tree is represented. So we will take one more example to understand this better. Because if we understand the problem, how is it represented and how we can deduce the tree back from the array, our half of the problem will be solved. And then we can understand how to approach the problem. Okay, the what we have to find in this given tree is the degree of the tree. How is the degree of the tree defined? Degree of a tree is the maximum degree of all its vertices. So if you see for one, the degree means with how many elements it is attached to. So if you see one is attached to only three. So the degree of this particular vertex will be one. If you see about three is attached to one, two, three of his sub children and one of its parent. So the degree of this vertex three is four. Again, the degree of four, this particular vertex will be one. Why? Because it is connected to this one vertex three. Similarly, the degree of this will be 1, the degree of 5 will be 1. So what will be the maximum degree? It is 4. What is the degree of 4? Like vertex 3 has the degree 4. So if you see this same example is given in the input over here and the output is 4. Okay, as I said, let's take one more example of this array and see how we can represent a tree based on that. Then we can approach the solution. We can discuss the approach, how it will be. So I will quickly take an example. So I am taking an example. Let's say our tree is represented something like this. 3, 3, 2, then 4, 5, 5, 6, 6, and then 4. Okay, so this is our tree right now. Let's understand how we can make a tree based on this array, and then we will see that how to how to solve this particular problem, how to get tree from this array index, and then we will understand how to approach the solution. So this is our tree. Okay, as we discussed, one will always be the root. You can see in this given example also, one is at start and one is at end. So let's make one. So one R1 is here. Now, as we discussed, that all the other elements over here, all the other elements inside one will be its subtrees. But we don't know how to place them, how it will be. But if you see that these 3 and 3 are again bounded under these two, okay? It means these 3 and 3 will be the subtree of these two, but not the direct children of one. So, but we are sure that since these two lies directly inside one, it means the two is a direct child of one. Okay, let's skip the inside elements for now. And let's, when we go in this four, we again see that this four starts here and ends over here. So we can understand that four is again a direct child of 1. So we can deduce by here that 4 will be a direct child of here. Okay. Now we see that 3 is basically wrapped under this 2, directly wrapped under these 2. So we can understand that 3 is a child of 2 basically, right? Again, this 5 is directly wrapped under 4 and there is no element between 5. It means 5 is a leaf as well as 5. Who is the parent of 5? 4. So parent of 5 will be 4. Again, if you see the 6, 6 is directly wrapped under these 4s. So we can say that the parent of 6 is 4. So parent of 6 is 4. Okay, so this is how we can build a tree based on the given input, based on this given input. Now, if we try to understand, if we just make an analogy, so we will understand that the elements which has no elements between them, means it starts and the adjacent element is same, they are the leaf of the tree because they don't have any child. So C, 3 doesn't have any child because there were no elements. So it is 3 over here. Again, similarly, it holds true for 5 and it holds true for 6 as well. They were child. Who are parent of the particular element, we can understand based on who is wrapping that. So if you see 3, these 3 were wrapped by 2 as well as 1. But it means that 2 is directly wrapping it 2. It means the parent of 3 will be 2 and the parent of 2 is 1. So 3 is a subtree of 1 and the parent of 3 will be 2. Again, the same thing holds for 5 and 6. 5 is directly wrapped by 4. So we can say that 4 is the parent of 5 and 6 also is wrapped by 4. So 4 is the parent of 6. And what is 4 wrapped with? 4 is wrapped with this one and this one, right? So the parent of 4 is this one. So we got our tree, right? Okay. So by this, let's first understand this is how any tree can be made if we are given this array. Okay, let's get back to the question. Okay, so since this input will be in this format, in an array format, if we understand how a tree will look mentally, basically we can understand, we will try to figure it out, what will be the degree of any particular element. If we take what will be the degree of this 3, we have to find out. Okay. Similarly, what will be the degree of 4? We can find out. How we can find out? Let's discuss over here. Okay, so I will just try to copy this particular thing. I will start over. I will just simply paste it over here for now. Okay, now if you see that since since one is the parent and the direct child of 2, it has two direct children, 2 and 4. How we got to know? Why 3 is not the mm, child of 1, because 3 is wrapped with 2. So if we have to find for any particular element how many elements are directly attached to it, is we can start from here. Okay. Since we started over here, we saw that 2 starts over here and 2 ends over here. So we can say that, okay, we got a one element which is direct child of 2. Now we don't have to take care of this right now, because we are just right now taking into picture about the children. So in our mental picture, we can draw 1 and we can say that, okay, we got a 2. Now we will directly jump to the ending of the 2. So ending of 2 was this. So one element we fixed. Now again, we came to the next element, 4. Okay, 4 started. So it means that 4 is also a child of 1. We draw 4. Where is 4 ending? 4 is ending directly over here. Okay, so all the elements inside 4 are not the children of 1. So we'll skip all these elements for now and we'll reached here. Okay, then again we will move one element over here and we reached at the end of 1. So we got to know that 1 has two children. So what will be the degree of 1? The degree of 1 will be 2, because two elements are directly connected. Cool. Now let's try to understand what will be the degree of any other element. What will be the degree of 4? For that, what we will do, we will go to the starting of the 4. We went to the starting of the 4 and then we will repeat the same process. We will go from starting of the 4 till the end of the 4, because this will be our subtree. So what comes after 4? 5. So 5 was directly being wrapped by 4. So we can say that 5 is a child of 4. Again, since 5 came, now whatever right now, there is nothing inside 5. But even if there was something inside 5, we don't care about that right now, because right now we care about children of 4, right? So 5 was a child of 4. We will directly come to the end of 5 and we will reach here. Again, we encountered 6. So 6 was directly wrapped by 4. So we can say that 6 is a child of 4. Again, nothing is inside this, right? So we again came. Okay. Now let's take what was the degree of 4? So the degree of 4 will be the number of its children plus 1. What will be the plus 1 for? The plus 1 will be for its parent. So what's the degree of 4? So the number of children 4 had. 4 had two children basically, 5 and 6, and one parent. So the degree of 4 will be 3, right? Again, let's try to find out what's the degree of 2. So the degree of 2 will be number of elements, number of child of 2. So the child of 2, so we'll reach directly at the starting of the 2, and we will iterate till the end of 2, and we'll see what all direct elements are coming. So direct element that came was 3. So we made a child as 3. Okay. Are there any more elements? No. So what will be the degree of 2? Degree of 2 will be 1 plus 1 for its parent. So if you see, degree of any particular element other than the root will be the number of child plus 1, right? Because plus 1 for its parent, plus 1 for its parent, except 1, because 1 has no parent. 1 is the root of the tree. Okay, now quickly we can take one more example if we need, and then we will understand how to write the logic of this. So let's say I am writing 3, let's say 2 only for now, 2, 3, 4, 5. I'm taking a big example for now, 5, 5, 4, 3, 2, and 1. Okay, so we took this example. Let's try to build again the tree. Okay, so now if we take this, and now let's start from a random element. Let's start from 3 right now. So we have to build from 3. So what will be the children of 3? If we want to draw the children of 3, we have to start from the first index where we saw 3 till the end, because all the elements inside it will be the subtrees. So we saw that 4, we encountered a 4. It means 4 is a direct child of 3. Again, do we need to take care of 5? No, because 5 is not wrapped by 3. 5 is directly wrapped by 4. So we came across 4, and then we will reach at the end of the 4. Okay, we will jump to the end of the 4, and then we again encountered 3. It means that 3 has only one child called 4. Okay, now let's say we have to find the children of 5, let's say, for that. Okay, so let's say we made a 5. I made a 5. Now, anything coming under 5? No, right? It means there are no children for 5. There are no children of 5. Okay, we are not taking care of connecting it to parent, because somehow parent will connect to its child by itself. Okay, now let's see who are the children of 4. So if we have to find the children of 4, so we have to start at the first index of 4 till the second index of 4. And we saw that 5 is directly coming under this. It means 5 is a direct child of 4. Okay, and 5 came, we jumped to the end, and we saw 4 again came. It means the subtree of 4 has been ended. Okay, now let's see about 2. Who are the direct children and who is the subtrees of 2? So if you see, which all elements are subtree of 2? 3, 4, and 5. But which is a child of 2? For that, again, we will use that approach. We will go to the first index of 2 till the second of index of the 2, and we will start iterating. We will start iterating for this particular subarray. We encountered 3. It means for 2, 3 is a child. Since 3 is a child, now whatever 3 is wrapping inside it will be the children of 3, and it will be a subtree of 2, but not direct children. So from 3 to this 3, we directly jumped, and we went to the next element, and we saw the second 2. So we will stop that. It's done. What's left now? The only thing that left is 1. So 1 has a, we'll start from the first encounter of 1 to the last encounter of 1, and we encountered 2. It means 1's direct child is 2, right? So one's direct child is 2, and whatever inside 2 are the children of these 2. So we don't need to take care of that, because while building tree, we only care about the direct children. So from this 2, from here we started, we reached here in this 2, and we directly came to this end. Okay, again from here we again encounter 1, so we'll stop our finding, and we finally built this tree, right? And while doing this, I saw that 4 has one child. So the degree of 4 will be, in bracket, I can write 2, because one child and one parent. Again, for this, the degree was 2. One child, one parent. How many child 2 had? 1. Okay. So the degree will be 2. One child, one parent. Since 1 is the root of the tree, what will be the degree? Only 1, because only one child, there is no parent, right? Okay. So this is how we will approach the problem. We will pick an element, we will iterate from start to the end, we will count the number of children, and we will add 1 to that. So the number of children plus 1 will be the degree. Let's try to code this part. Okay. So for this particular illustration, I will use C++ language. Okay. Now in this, to represent a tree, we have to take input, output by ourselves only. So if we see the input of this, I will open this in a new tab, and let's read the input of this tree. So in the first line, there will be T, that is the number of test cases. In the second line, or we can say the first line of the first test case, there will be a number n that will represent the number of vertices. So for example, here the vertex was 5, because in this graph there are 5 elements. So the second line will have 2n integers. It means this array we will take as input. So let's try to do that. Let's try to take input for now, and then we will again start discussing the solution. So as discussed, let's input a t as a input, the t equals to number of test cases, and then let's take the input quickly. Okay. Inside this, there will be an input for integer n. We will take integer n. Integer n is number of vertex. Now we will quickly declare a array. Let's use vector for now. And to do that, we will include vector. This is language specific. If you are doing in Java or Python, you won't require vector. You will require some array data structure. Whatever you are comfortable with, it does not matter. Okay. Now for those 2n elements, since those are the number of elements for that, so we'll take 2n number, and we'll iterate over it, and we will put it in our vector. So let's say for now, I'm just taking this in a temp variable, and I am doing it and pushing it to the array. So basically, okay. So by this line, till the end of this line, we would have taken our input, right? The whole input. Now, since we have to now do our calculation, so with each test case, let's say I will create a separate method where we will do all the calculation to keep the code decluttered basically. And I will pass this array, and this will calculate, and this will print the maximum degree for that. Okay. So for now, our work for this particular main method is done. Here we have taken our input, and we are passing it to a variable method basically, and there we are doing our calculation to find the maximum degree. Okay, let's define our method. So our method name was find max degree. Let's initialize it. Let's take the array as input. Okay. Now to store this. So as I discussed in the graph, we need to iterate from one. We will start from one, and then we will keep iterating till the end of the one we reach. Or let's say for this particular three, we have to iterate, we have to find its children basically. So from where to where the children are available, from the starting of three to the end of the three, whatever are inside is a subtree, and whatever is direct is a child. So what we will do, we will store the first appearance and the second appearance of three somehow. So we can do it in multiple ways. We can keep a left and right array where we will store the appearances. For the simplicity, I will use an unordered map. So let's include an unordered map also. So I I will just initialize the map. This I will keep the data structure something like this. So what this means, that this map will have a key value pair. The key will be the vertex. So let's say the vertex will be 3, and then we will store the appearances, the indexes. So for 3, this first element will be the first appearance, and this second element will be the second appearance of this map. Now let's fill this map. Now let's fill the locations, the positions of the elements. So I started over here, till my whole array size, I will start. So till my whole array size, I will. s- Now for this, I am saying that if my map already has that element, if my map has uh, this element, it means that I am encountering the first element, or I'm encountering the second element. So if my map already has that number, it means I once I have encountered that element, and now what I'm encountering is the first index. So I will do that like this. First, and then I will keep second element. So this so with C++ map, unordered map, if you know, you will understand that with this logic, we basically check that if the element is already present in map, it will not return map.end. So we are keeping the first element here, first appearance here, and I as the second element, and we can say that, okay, this was the second appearance. Else, if it is we are encountering for the first time, it will come in this else part. And here we can say that this is something like I and -1. -1 will be just a placeholder because every element will at least once encounter, like at both of the times, it will encounter the first and the second element. So for the first time, map will go over here, and the second time when the same element is encountered, it will go here. Okay. So by this way, we have collected the data in our map. What is this data? The data is about appearances about these all vertexes. Like one appeared at zeroth element, and let's say it appeared at ninth element, basically. So in our map for one, corresponding to one, we would have stored 0, comma 9. Again, for 2, what would we have stored? For 2, we would have stored 1, comma 8. Okay. So this is how our map we have structured. We have created our map. Now we have to print an the answer will be the maximum degree. So for now, let's initialize, let's call it answer only. So now what we will do, we will start from vertex 1 and we will go to the end of the total vertices and we will count the number of children plus 1. We will basically count the degree of that particular vertex, and whichever is the maximum, we will start storing. So what I'm doing, I am starting from 1 because vertex starts with 1, and I will end it with temp with my array dot size. So what is my array? So if the total number of vertices are n, so the array size will be 2n, right? That's why I'm doing divided by 2. So if the total size of the array is 10, it means I have to go from 1 to 5. And I will do for each of the vertices and I will keep finding it. Okay, now our task is to find the child. Now for the number of children that particular vertex I represents, how many children it have. So to count the number of children, let's initialize a variable for now and let's start. So this is the whole logic right now what I am writing, what we discussed. What we discussed basically, whatever, if we have to find the number of children for 3, for the number of children for 3, I will copy this and I will take it in another example and again quickly discuss this. Okay, it's okay. I will take one example. So let's say 1, 3, 4, 4, 5, 5, 3, 1, 3, 2, 2, 1. Okay, let's say this is my example. Now, if we have to find the number of children of 3, what we will do? We will pick the first element. We will start iterating from the first element till the second presence of 3, and inside whatever is there will be the subtree of 3, and if that element is directly mapped under 3, it will be children. If there will be, let's say for example here there must be 6 comma 6 for example, then we won't take care of this 6. We will say that 6 is the subtree of 3, not children of 3. So we will see just 4 and we will directly jump to 5. So what I will do, I will start and I will say that I will find the first appearance. How can I find the first appearance? I can find it by map of I dot first. So in this map, we already know that map dot first will be the first appearance. So from there, I will start one element ahead of that. I will keep iterating till the second appearance of that. Okay, I will keep iterating till the second appearance of that. Okay, and I will keep finding the children. How to find the children? First of all, since from this to this, if we started, one child is encountered, right? And we will say that now we will directly jump to whatever the child we encountered, the end of that child. The end of that child will be this array j dot second. I will again explain this how and what is happening right here. So if you see that map of array is this and then this, right? So what I mean to say that since this is my, let's say, index 1, vertex 1. So for vertex 1, I started with from where it starts till to where it's end. In the middle, we encountered, let's say, for example, in this, for 1, I encountered 3. So what will I do? I will make a plus 1 to the child. I will know that, okay, 3 encountered. So in my count variable, I will keep a plus 1 and I will find the second appearance of this 3. What is the second appearance of this 3? How we can get it? We can get it from our map. We can get it from our map. So we can just do map of 3 dot second. If I just do that, I can find, right? Map dot 3 dot second. I will reach here. Then I will again start from here that, okay, I reached here. Now I will start from here and again find the other children of 1. So 3 was one children. I bypassed till 3 and then I encountered 2. So I will say 2 is one more child. I will again do a count plus plus. I will increase the counter and I will reach here, right? So that's what I am doing. I started from the element. I will iterate till end of that element. I am increasing the counter for each child. And what I am doing, I am again going to the second uh, presence of that particular element. And again, as I said, for every encounter, if the if the vertex is not one, it means we need to add one more to its count. It means for its parent, right? For its parent. If that is one, then we don't need to count. If that is one, then we need to count. So in that case, we'll just update our global answer variable, which is the answer, which is the maximum degree. We'll do a max of whatever we encountered till now and what we'll do there. So if that is the correct count is greater than answer, we will get this. And here we will just print. So this whole iteration will start from 1 to, if the size of the array is 10, so we'll 1 2 3 4 5, we will do an iteration like that, and in that we will find number of children for each of the element, each of the vertex, and we are doing a plus 1 if that is a non-root element, and we are updating our answer. And at the end, this whole iteration will take care of everything, and we can print our print our answer. Okay, let's try to test this. We There might be some issues because there were no ID support or something. So if something is encountered we did not see, we can again look into it. But seems 5 test cases have run. 8, okay. 10. Okay, it got accepted. Cool. So again, I will quickly give you an overview of that, and we are done with this problem. So what we did, we took an input. This is pretty straightforward, and whatever the calculation is inside in this function. In this function, what we are doing, we are creating a map where we are storing all the first and second occurrences of each vertex. This key will be the vertex, and the first and second appearances I will store over here. I built this map to store that, and then my logic resides here. What is the logic? I will iterate through each of the vertex, and what I did for each vertex, I found the child. Okay, I found the one child. I am increasing the counter, and for that, I am going to the end of that child, because inside the child, whatever is present, it's not its child, it's just a subtree. So, and the same way, we will keep iterating, we will keep finding the number of children, and we are doing that. Okay, so this was it. This is the diagram that I used to help you understand that problem. I hope it was clear. Okay, so this was it. Thank you.